Okay, so the last thing that we're going to do related to the carbon cycle is the greenhouse effect. Okay, have you guys ever been in a greenhouse before? Yay, nay? Okay, it's really hot, right? It almost feels like it's being heated in there, but it's actually not. Do you guys know what's happening? Usually they're made of glass or sometimes they are made of plastic, but do you guys know how that works? Well, yes, plants grow, but heat is being trapped. Okay, when the infrared heat is traveling in, it's at a higher energy because it hasn't made contact with anything yet. So it's high energy enough that it can go through the glass or the plastic of the greenhouse. But once it bounces off of the surface, it loses some of its energy and it's reflected off the glass or plastic and it traps the heat inside the greenhouse. And that's why the greenhouse is a lot hotter than the surrounding area. We also have something similar happening on Earth. It's called the greenhouse effect. Have you guys talked about it, heard about it? I feel like you probably have. Okay. And so with the greenhouse effect, instead of having this layer of glass, we've got a layer of gases in the atmosphere called the greenhouse gases. And those greenhouse gases work the same way. The heat, the infrared rays can travel into the earth, but once they bounce off the surface of the earth and are reflected, they run into those greenhouse gases, and the greenhouse gases deflect them back towards the earth, trapping the heat. Okay, what this has to do with the carbon cycle is the greenhouse gases are primarily made from carbon-based molecules. Do you all know what the greenhouse gases are? There's three big ones. Carbon dioxide is one of them, methane, and water vapor. Water vapor, we're not going to discuss as much right now, but carbon dioxide and methane are both carbon-based, and their storage in the atmosphere is being accelerated by human activity. Okay, climate change is caused basically by a beefed up greenhouse layer. We're putting more CO2 and methane into the atmosphere, and that is causing more heat to be trapped on Earth. Because I feel like you guys hear a lot on the news wherever, like burning fossil fuels is leading to climate change. But we don't always make that connection for you of how. And that's what I want to do today before we talk about the effects. The reason burning fossil fuels contributes to climate change is because you're putting more CO2 molecules into the atmosphere. Remember, there's several ways that CO2 can be returned to the atmosphere. Can you name some of them? Burning fossil fuels, respiration, not yet, decomposition, and weathering all return it. Photosynthesis is the only thing that can remove carbon. So it's already kind of out of balance, right? There's 4 ways to put carbon in. There's only one way to pull carbon out of the atmosphere. And then we've added to that by accelerating burning. We're burning more fossil fuels. And it's not just anything that's carbon-based. When it's burned, releases CO2. So that includes the carbon being released like from forest fires or when we intentionally burn anything, trash, for example, it releases carbon. Okay, so that's one part of it. The other thing, methane comes from where? No. CH4 comes from cow gas, okay? So when cows burp or pass gas, they release a large amount of methane. And because we are so dependent on dairy and beef, if you look over our dairy and beef farms, there's huge clouds of methane that are a result of there being more cows because we, like I said, eat more dairy and eat more cows. So that's another way that we contribute by the food choices we make. And then the third way that we contribute is as the human population grows, we need more space, right? And to make that space, we cut down trees. And what can trees do? They can bring back the CO2, they can do photosynthesis, and they also store carbon. So when you cut them down, when you cut down a tree, it's got to be disposed of somehow, and that's releasing carbon. So those 3 things, deforestation, burning of fossil fuels, and red meat consumption and dairy consumption are driving an increase in CO2 in the atmosphere. And we can track this using historical data from ice cores, we can trap the temperature in CO2 over time. And this really picked up during the Industrial Revolution. Why? That's when we started to burn more fossil fuels for industry, okay, and also for our own transportation. So all of those things contribute. But today, from the trains as well, today what we're going to try to do is just make sure that we understand how the greenhouse effect works. So I've got this short video for you. I'm going to stop it in a couple different places to talk on it because it goes so fast. This is called In a Nutshell, because it explains it to you very concisely and quickly. So we will pause and go over it as you guys are watching. So just listen and follow along and write your answers down, and you should be good to go.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable negative 18 degrees Celsius, and even deadlier, they range from negative 170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere...
Okay, I've paused here so we can go over the first two questions. What prevents the Earth from being as cold and as hot as the Moon is our atmosphere. The atmosphere prevents us from having extreme temperatures and from having extreme temperature fluctuations from day to night. So on number one, your answer is atmosphere. And then for the second one, it acts as a shield by blocking out the harmful UV radiation, and as a greenhouse by trapping the heat radiation coming in from the sun. So a shield blocks the harmful radiation, and the greenhouse layer, the greenhouse gases, trap necessary heat.
Atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds...
Alright, I'm stopping here to discuss your next questions. We did not answer number 4 as a class because it's also related to number 3. In the video, it talks about electrical lopsidedness, but in chemistry and in biology, we call that polarity. So for example, if you look at a water molecule, the oxygen is so much larger than the hydrogen that the positive nucleus of the oxygen draws the electrons closer to that side. Okay, so it causes polarity. It causes vibration and movement in the molecule, which allows the greenhouse gases to both absorb and then reflect the radiation that's coming in. So it's a little bit hard to understand, but basically it's the vibration and the movement of these molecules. And what I'm pulling up now is just another little demonstration of it zoomed in. Here's your carbon dioxide molecule. Okay, the infrared radiation hits the CO2 molecule, it absorbs it, and then it reflects it back down to the Earth. So it's the vibration of these molecules the movement of these molecules caused by polarity or movement that allows greenhouse gases to trap heat.
Kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
Okay, so I wanted to back it up here so you could look at this analogy again. I really love this analogy of the pinball machine. The heat waves, the radiation waves are the pinball, and the surface of the earth represents those flippers down there at the bottom. So the waves hit the earth just like a pinball hits the flippers in a machine, and that pushes them back out towards the atmosphere. The greenhouse gas molecules act like bumpers or obstacles in a pinball game that reflects the heat back down to earth, much like those bumpers and obstacles would reflect a pinball back down to the flippers in the machine. So the reason the game is much, much harder to play today, you can see in this picture that the heat waves, sometimes they're going to hit a greenhouse gas, but eventually they are able to slip out through the spaces that you see there. Okay, but now as we add more carbon dioxide to the atmosphere, that layer has become thicker. There's more obstacles that the heat rays may encounter upon exiting, like you see in this video here. There's more gas molecules, more obstacles for the heat waves to run into as they're exiting, and as a result that is trapping more heat here on Earth. And you'll see in the Edpuzzle that you're going to watch, or maybe you've already watched it, that the temperature has been raised about 1.5 degrees Fahrenheit, which sounds really small, but that is a global average. Some areas are warming faster than others, and just that 1 degree change has been a lot to have effects such as melting ice caps that are causing sea levels to rise. And in our next lesson, we are going to learn more about some of the causes, effects, and interventions to climate change when we watch the Beyond the Flood documentary. So that's what we're going to do next, or I'm sorry, before the flood, not beyond the flood. So that wraps up our greenhouse effect lesson. You should be able to answer that last question on the paper now.